Okay, well, let's draw an isosceles triangle just to get us started. Um, an easy way to do that, of course, is to use your compass in the definition of a circle. Just choose 2 points on that arc. And we know that the two radii, of course, are going to be congruent. And we've got an isosceles triangle. Okay, so there we have it. We'll mark this up. So what do we have given? Um, triangle ABC, isosceles, prove base angles congruent. Let's draw a proof diagram of this. So, at first glance, it's just like, well, shouldn't this just be obvious? Like these two angles should be congruent because they sort of open up to sides that are exactly the same length, right? But of course, it's not given in the definition of an isosceles triangle that these two angles are congruent, so we really do have to prove it. And the thing that sort of strikes me is that, the triangle has some symmetry about it, right? I mean, there's a line of symmetry, and so if we can get sort of the triangle congruent to itself, in other words, if I can prove that triangle BAC is congruent to triangle CAB, then that will map angle B to angle C by corresponding parts and prove that they're congruent. And of course, to me, it seems like it's fairly easy to do because BAC has in it a side, an angle, and a side, and CAB has in it a side, the same angle, and a side. And since these two sides are given as congruent, then certainly BAC is congruent to CAB by side, angle, side. So we just have to put that down, I guess, or I guess make sense of that to our reader. So let's just kind of draw a diagram of how, that logic will go. So here, I guess we'll start with the givens. From the givens, we know that triangle ABC is isosceles. And then we know that that means by the definition of isosceles triangle. So usually I put these boxes in. These will be like in your reading what they call the proof blocks. So this is the piece of known, I guess, um, um, I guess a piece of known knowledge that we're applying. We can say the definition of isosceles then tells us that it has to have at least two congruent sides. The sides that we have congruent are AB and AC, right? So we know that AB is congruent to AC, and well, it doesn't matter what order, or you could say reflexivity if you want, but I'll just say AC is congruent to AB as well. So those two sides in any order are congruent to one another. And then we have to have an angle in two triangles congruent. So we're going to use angle BAC, which is given in the drawing. So in the drawing, I mean, this is a given. Sometimes, people will say given to get started. In the drawing, we have what angle BAC. But if we apply reflexive property here, which again is a piece of prior knowledge, we can say that angle BAC is congruent to angle, let's do it the other way, CAB. So now we have a side congruent to side, a side congruent to side, and a contained angle congruent to a contained angle in two triangles. The triangles are BA to AC and CA to AB. So we can use each of these guys and apply side angle side triangle congruence to get out that triangle BAC is congruent to triangle CAB. So those two triangles are congruent by side angle side. So you can just check this to see that this makes sense. The first side is BA here, so that corresponds to AC here. The second side is AC here, right there, and that corresponds to AB here. And then the angle BAC, there it is, corresponds to the angle CAB there. So you can see that indeed the side angle side has been satisfied and the ordering is correct in terms of the way I've written the triangle congruence. And what's nice about this is that now we can see angle B and angle C correspond, and we know that by CPCTC, corresponding parts of congruent triangles, that that I can invoke any angle. B could be congruent to C, A congruent to A, B congruent to C. But of course the one that we're really after is just angle B. So I'll write down angle, let's see, ABC congruent to angle ACB. And that's really what we wanted to show, right? And so you can see that I really like these diagrams. I hope you do too. They really give you a sense of the structure of the proof and what has to happen. There's really kind of two lines where information comes from, or I guess two roots maybe, for the conclusion. And the two roots are, you're starting with an isosceles triangle and applying the definition of isosceles to get a couple sets of congruent sides, I guess written in two different orders. And then you're identifying an important angle in between those two sides and showing reflexively that it's congruent to itself in a different order. And that allows us to invoke the side angle side triangle congruence to get the triangle congruent to itself in a different order, which then allows us to get two angles that are, the ones we're after, the two base angles, congruent via CPCTC. So that's sort of interesting, right, to see how this works. So that's the idea. Let's go ahead and write I guess a paragraph proof of this. So let's go ahead and make our drawing up really quick again, and we'll write the paragraph proof. So decent enough drawing, it seems like. I'll put my A here, my B here, and my C here. Two congruent sides I'll just mark, but I'll say the only given really is that triangle ABC is isosceles. And we want to prove base angles congruent. Okay, so usually, we start with some sort of given and to prove or want to show. And then the actual proof, you want to demarcate, announce that here's my proof. What I'll say is, since triangle ABC is isosceles, we can say that two sides are congruent. And you can make up your drawing, say AB congruent to AC. I guess we could say by reflexivity, we also have angle BAC congruent to angle CAB. So BAC, CAB. these, I guess, two results are enough to give triangle BAC congruent to triangle CAB by side angle side triangle congruence. And this provides for, let's see, angle ABC, ABC, ACB by corresponding parts of congruent triangles. So ends the proof. So there would be a nice, I guess, paragraph proof of what we did here next door as a proof diagram. I mean, it's kind of neat to look at them both side by side. You know, we've basically done the same thing here as here, and we've just put this into a paragraph form. I do find it's easier for students when they first start out proving things to work this way first. I mean, this is almost like a logical rough draft, I guess, to a verbal argument. And you can definitely see that the important pieces are in there. You know, we've said by definition is isosceles. I guess we could say by definition. We can see the reflexive property coming in right here and here. We can see definitely that side angle side is invoked and that corresponding parts are invoked. So sort of the four proof cards that would be, or proof blocks that would be important in this proof or prior understanding are these four things right here. Without them, you really can't construct the proof. So I hope that gets you started on a first sort of easy proof. Once we have congruent sides, we can argue side angle side to get congruent base angles of an isosceles triangle. We're going to use this theorem quite a bit, so let's just name it right here. Let's call it the isosceles base angle theorem, or base angles of an isosceles triangle. It's a known fact now. You can use this in proofs from here forward in our course. All right, let's go ahead and move on and talk about one more example. So let's prove that the diagonals of a rhombus bisect opposite angles. So the diagonals of a rhombus bisect opposite angles. Put those off. Well, it'd be nice to have a nice picture of a rhombus, and lucky for us, we already talked about how to draw those. So let's go ahead and draw an arc with 2 points on the arc, and then off of those 2 points, 2 arcs as well, like that. That should be enough to give us our rhombus. Put a point there. There it is. Here's our rhombus. Let's go ahead and draw in a diagonal. Let's go ahead and label some. There they are. So given ABCD is a rhombus, let's see, what do we want to do? Show AC bisects angle what BAD and angle BCD. So how is this going to work? Let's start off from the beginning. So let's see here. So let's start off first with the definition of a rhombus. So we'll start off with A, B, C, D is a rhombus. If we apply the definition of a rhombus, what do we get out? We get out that what AB congruent to BC congruent to DC congruent to DA. Well, that's kind of neat, because what that means is that we definitely have congruent triangles top and bottom. I don't know if you can see this right away, but it looks like we get it by side, 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 because there's a shared angle here. So what that would mean is that these two angles, if we can get it by side, side, side in the right order, would be congruent to these two angles. So that works out really nicely. Okay, so here we go. Let's do it. We've got at least these two sides, and the correspondence is established here, but we need this one congruent to itself in both triangles. So what we'll do is we'll say AC is in the drawing. So we see AC in the drawing by reflexive property. We can say that AC is congruent to itself. So now we have three side correspondences. I guess AB to AD. So that's, sort of these two, right? And then BC to DC, so that would be these two. And then AC to itself, which would be these two. So that's side, side, side. If we add those guys together, I guess, using side, side, sorry, I just about put side, side angle. Still thinking on the last proof here, right? Side, 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 triangle congruence criteria. What do we get out? We get that triangle ABC. It's got to be congruent to triangle ADC. And then what do we get out of that? Well, by CPCTC, we get out that, let's see, BAC, so BAC is congruent to DAC, DAC, yep. And let's see, BCA, so that's here, BCA, DCA. And that's really what we wanted to show, right? So pretty neat that that works out. It's interesting here, and this might not be what we were asked to prove, but it turns out all of those angles are actually the same, right? In other words, they're not only congruent to each other here, but these two are congruent to these two over here. And we can see that's true if we would have applied the isosceles base angle theorem, right? And we know the thing's isosceles because of this line. So we could have had another branch off of here that says, well, triangle on top, triangle on bottom are isosceles. Isosceles base angle theorem says that those two angles are congruent. And then combining that with this and transitivity would then give the fact that all four of them are actually congruent. But we don't have to do that. We're not asked to do that here. We're just asked to show that, that the diagonal bisects these angles. Okay. Let's go ahead and write a paragraph proof for it. So we'll start over here again with our picture. Maybe draw a slightly different one this time just for fun. So something here. I don't know, pick those 2 points there and there. Get another that point right there. So given ABCD is a rhombus. Prove what AC bisects BAD and AC bisects angle BCD. So here comes the proof. If you're used to doing two-column proofs, go ahead and submit them for your homework. That doesn't bother me at all. But I'll continue to do a paragraph proof here. So let's see. The definition of a rhombus, this provides that, let's see what AB is congruent to BC is congruent to CD is congruent to DA. Reflexivity gives us that what AC is congruent to itself. Running out of lead, sorry. These results combine to how do I want to say it? These results combine to make clear that what triangle ABC congruent to triangle ADC by side triangle congruence. So by corresponding parts, of congruent triangles, we get, what is it, angle BAC congruent to angle DAC, and angle BCA congruent to angle DCA. And then maybe we should say which shows that the diagonal AC bisects angle BAD and angle BCD. So ends the proof. Okay, so again, kind of a, here's the blueprint, the design of the proof. Seems like it's fairly straightforward. Definition of a rhombus, reflexive property leads to side. CPCTC gives us our bisection. And then the way it would look sort of in hard finished form as a paragraph proof. And you can see the components are still in there. Definition of rhombus, reflexivity, side, and CPCTC. So the blocks, the important blocks are there. All right, let's try one more of these before we call it a day. So here we go, a little bit harder of a problem. Suppose that points A, B, C are distinct points on a circle with center O. Prove that the measure of AOC is twice the measure of angle ABC. This one is probably a good one for us to turn to GeoGebra and take a look at before we dive right in. So I'm pulling up GeoGebra now, a little bit of GeoGebra training here. One thing you'll notice is that mine might look different than yours. So there are things you can do to change the way GeoGebra looks upon initial appearance when you open it up. Um, you know, for example, if if you drop down the graphics, you can turn on and off your grid. You can turn on and off your axes. If you right click on a white space on the grid and go to graphics view, there are ways that you can format the way this looks. So in particular, you can format, how you want to show or hide one of the axes. You can talk about tick marks. Do you want tick marks and minor tick marks? Do you want set tick marks at a certain distance or let it be automatic? You can also make these stick to edge, so you can stick it to the edge. I don't like that. And then you can sort of, play around with the grid. Defaults to show major and minor grid lines. I really don't like that, so I leave it at major grid lines only. And I do usually like my distance set to 1 by 1, so just unit grid lines or lattice points. Once that's done, one of the ways you can make this sort of be your permanent view is you can say save settings like this. And once you save settings, when you cancel, and I guess close and open again, those settings will be reloaded for you. So that's one way that you can customize GeoGebra to be sort of formatted the way you choose it to be when it loads. So you can see it again, looks just like it did. But let's go ahead and play around with the question. The question says start with a circle with center O. I also have options for labeling. I usually do no new objects because I feel like it over labels everything. Okay, so there's a circle with center O, and then we're supposed to pick 3 points on the circle, an A, a B, and a C, I think. I'm going to go ahead and hide the point that defines the circle, so that's B. And I'm going to rename each of these points. If you click on, I, by the way, organize by object type. I like that better than by layer. If you click on point, right click on everything and just show label, all the labels will pop up for those objects that are all points. This one I think I want to call A. So I just highlight it and type A and it'll rename it, and then A itself, which was here, will be renamed. I'm going to call that O. So there it is. And then this one we're going to call B. There it is. And this one we're going to call C. There it is. And we're supposed to take a look at these two, A, B, C, that angle compared to AOC. And supposedly AOC is double the angle ABC, which is kind of interesting to see. Let's try to see if that's actually the case here by measuring the angles. GeoGebra, of course, measures in a counterclockwise sense, just like on the unit circle. So I'll start with COA and measure that to be 126.47, and then CBA, and that's 63.23. And you can see it sure looks like the angle is doubled. There is a neat way, though, you can check this. You can see the angles are alpha and beta, and what we like to do is divide alpha by beta to see if it's 2. So down here is this thing called the input bar at the bottom, and I'm going to just go ahead and type alpha divided by beta. Now, how do you type alpha on a keyboard? Well, we can't. So over here on the right, you can see that there's a list of, I guess, symbols, and I'll do alpha and then divide it by and do symbols again, beta, and hit enter. And then I get a number out. You can see that number has been assigned a value. It's little a, and it's equal to 2. And what's interesting about this is that it doesn't change. I guess the number 2 here remains 2, which seems to mean that there's something very deep going on here. And what we would call an invariant feature of this drawing is that this number is always twice that number. Interestingly here, since only one of them is being changed, the other one has to maintain the same value, even though I guess the angle sort of looks like it's getting smaller, but it's not, right? 38.28, 76.56. The ratio of these two numbers is always 2. There is kind of a neat way that you can do this, on the dynamically here on the screen, and I'll show you that today. It's kind of fun to do. So in a text box, if I click on a text box up here, I can write, let's see, AOC, let's see, angle. So there are symbols here that you can use if you want. Let's see, I don't know if the angle one's easy to find or not. Sometimes these are hard to find in these. Did I pass it already? I hope not. Let's see here. There it is. So angle AOC, C divided by, and then symbol again, basic. No, it's in this one. Angle AOC ABC. Yeah, and then what you can do is you can actually pull in those angles if you want. Anything that's an object in the sheet can be used. Its value can be inputted here. So I'll put alpha there. You can see this is the preview, 76.56 divided by, and I'll put object beta next, and then I'll hit equal, and the object we want it to be equal to is A, which is 2. Hit OK, and you get this text box. Oops. That now can be, I don't know, probably made bigger. Let's make it a little bit bigger. There we go. But what's neat about this is it's dynamic, right? Look at that. Isn't that cool? So we can watch how those angles are changing over on the right rather than read on the left. But you get the idea. It definitely seems like we have some strong evidence that this angle here is always double this angle here. And the question is why? And that's the proof that we have to construct. So this is a fairly large proof because of the fact that there's 3 different ways this can sort of break out, right? This central angle is what they call this one in the middle, can be contained within the inscribed angle, which is this one that they call, the smaller one that's inscribed on the circle. So we have this situation where the central angle is contained within the inscribed angle. But then, of course, the central angle could be outside of the inscribed angle, so something like this, right? And you can see that the quality still holds here, that this angle is is double the value of this angle. So what's kind of curious about this is that there might be one proof for this case that won't satisfy, I guess, a logical argumentation for this case. So this is a classic case in geometry where the proof has to, have various stages or cases, right? There is the case where the central angle is inside the inscribed angle, where the central angle is not contained by the inscribed angle, and then the last case is this one where the central angle is actually on, right? The inscribed angle or array of the inscribed angle. So inside, outside, on are the 3 cases that would have to be proved. So let's just do one of them today, and I'll leave another one for homework. We'll do this one where the inscribed angle is contained within the central angle is contained within the inscribed angle. I'll leave this one for homework where the inscribed angle does not contain the center of the circle. And this one I'll just leave for your curiosity. Anyway, let's go ahead and move over to the ElmoCam and see if we can get a sense of what's going on. So let's go here and talk about this particular problem. So, some problems that are difficult, like this one, you can't just sit down and prove them. You have to sort of play around with it a bit to see if you can figure out what's going on before you even sit down to try to figure it out or to try to make a formal proof. So I'm going to do that today. I'm going to show you the way, I guess, model the way I would think somebody would have to do this if they didn't have any idea from the get-go what to do. So the way my mind works is right away I see this and this, right? And I think, okay, those are radii of a circle. What I'm trying to show is that this angle, right, is this guy is twice this guy. So those are the 2 angles in question that I really want to know how they're related. Let's go ahead and label up the same way we have before, AOCB. So So that's what we have. I see nothing that's going to help me. We know lots about triangles, so I'm going to make triangles. The first triangle I would think to make is this one. I see that it's isosceles, so its two base angles are going to be the same. I'm going to call them A. There they are. Um, oh, that's interesting because if these two are radii, I can make another radius here if I wanted to. I'll draw it out. So that guy's the same. So that means these are all three isosceles triangles. So that means if this guy's, say, angle B, that'll be angle B. If this guy's angle C, then that one would have to be angle C. And now I'm kind of starting to see like, oh, there's some interesting things going on here. I know that this guy right here, the one that I'm sort of after, is going to be 180 minus 2a's, right? Do you see that? Because this triangle has 180-degree sum. So if I can show that B plus C is 180 minus 2a's, then I'm done, right? And I kind of can see that there's a whole bunch of triangle angle sums in here, but I think the right one to do is the big one. Because in the big one I get a B plus C here, and I get C's and A's and B's and A's here, and that might be allow me to sort of somehow squeeze out that B plus C is equal to 180 minus 2A, or sorry, is half of 180 minus 2A, right? That would be the idea. So let's go ahead and see what happens here. So the triangle angle sum says A plus B plus B plus C plus C. So what it would be 2A plus 2B plus 2C equals not 360 but 180, right? And what I want to see is what B plus C is here, right? So I'll kick the 2A over there and get 2B plus 2C equal 180 minus 2A. And wow, there it is. You see that? 2B plus C's is going to be equal to 180 minus 2A. So in other words, if I double B plus C, I get the measure of this angle, which is 180 minus the 2A's here because of this triangle angle sum. So that seems to have pointed the way toward a proof. Let's go ahead and write a proof diagram, and then we'll conclude with a paragraph proof. Okay, so I hope that I'll provide this for you, but I hope that gives you a sense of sort of scratch work and this idea of idea generating to try to find a method to prove it. Okay, so let's go ahead and draw it up again. Pick an A, a B, and a C. And then I'll draw in some important pieces here. So I guess what are we given? I don't know, we'll call it M. Circle M, A, B, C on M, center O. What do we want to prove? We want to prove that 2 times the measure of angle ABC is equal to the measure of angle AOC. Okay, so let's see what we do. Let's see. So let's see. Since A, B, C on M, if we apply then the definition of a circle, what do we get? We get that OA congruent to OC congruent to OB. I guess we should probably say, draw OB. So that really helps, I guess. And let's see, what else do we have to draw? Draw AC. And let's see, we're going to apply the definition of isosceles. I could never spell that. And really we're going to say definition of isosceles and I guess isosceles base angles. We're going to use both of those, I guess, in turn. To state that the base angles are all congruent. I think we'll stick with our, we'll call these guys A. I'll just say angles marked A, B, C are congruent, right? Okay, so we've got that. And then let's see, we're going to use the triangle angle sum. To produce two different equations, right? One of them is this. It's what? 2a plus 2b plus 2c equal 180. And this is in what triangle ABC. So that's this one. And then this one we're going to do let's see, I guess we'll call it AOC. Measure AOC plus 2a's equal 180. So that's in this little triangle up here. And that's in what triangle AOC. And then what do? We do some algebra, right? We get 2 times b plus 2 times c equal 180 minus 2a. And then the measure of AOC equal 180 minus 2a. And then I guess we should probably replace this guy. 2b's plus 2c's is the same thing as 2b plus c equal 180 minus 2a, which is really 2 times b plus c is abc. 180 minus 2a. And then it's transitivity, right? This guy together with this guy with transitivity. Because if this is congruent to that and that's congruent to this, then this are equal to that, and this is equal to that. So it's a transitive property of equality rather than congruence, I guess. We get that that the measure 2 times the measure of angle ABC is equal to the measure of angle AOC. Sort of butchered this a bit because it's getting a little bit tight, but I think it works. Let's go ahead and use it as our template. It's kind of neat to look back. You can see definition of circle, isosceles triangles, and isosceles base angles come into play. And then triangle angle sum twice yields two equalities, both of which can be solved for the same quantity, which means by transitivity that they're equal, and it just so happens that we get the double sum that we're looking for, or I guess the double value that we're looking for, the 2b's and the 2c's, which is kind of cool. Like the 2b's come from here and the 2c's come from here, it seems like. I've seen other proofs of this, by the way, in case you're curious, and I've seen some proofs that rely on sort of an argument around this point and 360 degrees around this point. But so by all means, this is not the only proof, of course, and one of the neat things about proof is that there are different paths to the same endpoint. So if you saw something different or if you can prove it a different way, go for it. All right, I think we've got enough to write a paragraph proof. It's going to be a little bit Yeah, let's go ahead and draw it up. And all right. So we're given that, I'll call this M, circle M, A, B, and C are on M. O is center of M. And what do we want to prove? 2 times the measure of angle ABC is equal to the measure of angle AOC. And here comes the proof. I think what we're going to do first is draw in segments AC and OB. So we'll do that first. I always usually use my drawing to help the reader understand, so I add segments. It's kind of hard, because in a final proof, you kind of want to see what was added, what you started with. So sometimes people will make a copy of this drawing down here to show sort of how the drawing sort of accumulates objects, but in this case I think I'm going to just go ahead and add it. Okay, so we're going to draw in AC and OB. I'll just say by the definition of a circle, we get that OA has got to be congruent to OC to OB. So that makes 3, they're not congruent though, just 3 isosceles, I almost said isosceles triangles. Triangle AOC, triangle AOB, and triangle BOC. By the isosceles base angle theorem, angles marked A are congruent, so are those marked B and C. So we'll go ahead and put those in: A, B, B, C, and C. So there it is. Now I guess we've gotten sort of to this spot in our template. I guess really to this spot. Now we're going to invoke the triangle angle sum, and we've got kind of 2 places to do it. I'm going to do them in turn. I'm going to first do this piece and then do this piece and then bring them together at the very end. So let's go ahead. I'll say focusing on triangle. Let's do the small one first, AOC. We can see that by the triangle angle sum theorem, the measure of AOC plus 2A is equal to 180. This can be rearranged to get And this is kind of important, right? The first piece that we want is AOC equal to 180 minus 2A, right? AOC equal to 180 minus 2A. So I'm going to actually highlight that as the measure of angle AOC is equal to 180 minus 2A. And then I'm going to give it a name, right? I'll call it equation 1, right? Because I'm going to sort of shift now. I've got, sort of the first piece I need, AOC equals 180 by minus 2A. Now I got to go over here and do this one. So let's see, focusing on triangle, the big one, ABC, we can, and really this is a parallel argument, so I'll just say similarly apply the triangle angle sum theorem to get, let's see, I mean, maybe what we should do is do it in order: A plus B, B plus C, C plus A. A plus B, that's this one up here, plus B plus C, that's that one right there, plus C plus A. That's all got to be 180 because we've got a, which is just, if we put the two A's together, the two B's together, and two C's together, we get 2A plus 2B plus 2C equal to 180. And then what we want to do is we want to rearrange it. So we'll say which can be rearranged to get, what we want is we want that B plus C piece. Sorry, you can't see it. The B plus C piece alone. So that's what I'm going to do. I'm going to put the B plus C and call it 2. B plus C. And that's going to be equal to 180 minus 2A. And then really, which is just 2 times the measure of angle. B plus C is ABC. And that one I'm going to call equation 2, because now what I'm going to do is I'm going to make an argument about equation 1 and equation 2 and transitivity. So applying the transitive property to equations 1 and 2, we get 2 times the measure of angle ABC is equal to the measure of angle AOC, and that's exactly right what we wanted to prove. What we wanted to prove. So ends the proof. There it is. So again, I think the real important part here is to realize that, a lot of work goes into constructing a proof. First, you got to sort of sniff it out and play around with values and sort of try to see your way through the woods. You can't just sit down and write this sort of thing, right? Once you sort of think you found a way through it by just puzzling through it, using scratch work, then I think the right thing to do then is to sit down and construct what we call a proof diagram, or in the thing that you are reading this week, using things like proof blocks, these known squares. These are artillery proceeding from givens and things that you can draw or construct to a place where the conclusion emerges. So once you have the template, then I think it's fairly easy to sit down and write out, I guess, verbally what it is that your argument becomes finally. So kind of a 3-step process, I think, for these harder ones, right? First, start with some sort of a scratch work, then move on to a diagram, and then try to conclude with some sort of a paragraph or two-column proof. All right, well, I hope that you've enjoyed that, and you have some exercises to try out this week that are like these, and wish you luck, and let me know if you have any questions or concerns.